great.
Oh.
No.
Good morning, everybody. Andrew, Emily Rose, sit down. Hey, shut up, it's my time. I know, close this phone. How are y'all? Welcome back to Galois. Good morning, everyone. Welcome. Gosh, you got me all flustered. Good morning, everybody. Welcome back to Galois Theory. How are y'all doing this morning?
Woo!
Did y'all have fun eclipsing yesterday?
Yay!
Yeah.
Glad to hear it. Plan for today is we're going to talk some more about normal and separable extensions. More about normal, separable we haven't discussed at all yet. And then get into a really fun example that'll take us probably a full class to do because it's an involved one.
Well, that sounds something catalog.
I've got my usual office hours this afternoon, 1 to 2. Tomorrow, 11 to noon, 1 to 2. Homework. Originally I wrote nah, and then I decided I'm going to change my mind. I changed my mind on this.
You're not.
Oh.
Is it posted now? Wait, 2 days from now?
Dude, that's kind of legendary. Oh, wow.
Okay.
All right, enough of you have asked for an extension on this. I'm just going to get the whole class in 2 days. Especially because I think a lot of you wanted to come talk with me in office hours and set up appointments, and I don't. And honestly, I'm not sure how much time exactly I'll have this afternoon, so I'm just going to give you all a couple extra days. I will not have time to do any grading on this before Thursday, I assure you, anyways.
Well, you can
So,
have mine or I'll forget it on Thursday.
Say what?
You can have mine or I'll forget it on Thursday.
Yeah. If you want to, if you're all done now, feel free to turn it in. Otherwise, you can have till end of the day Thursday. Just because it seemed like I was getting more questions and more panic than usual over emails and students coming by. And Eleanor, who sent me 6 emails yesterday or something about it.
I think it was only 4.
Okay, whatever.
That's still.
I probably got 10
You can get one
total
from
from the
me.
class.
Oh, you answered my question, but I did email.
Well, I'm not going to say who all was emailing me, but there was a lot of.
I also had to go to your office hours for it, too.
Yes, and then there's this guy. So long and short of it is, let's just make it easy on everyone. Have a couple of extra days. If you're done with it, great. Otherwise, homework 7 will probably go up on Thursday to be due Thursday a week. Is the plan. And it'll be another it'll probably be I'm thinking a 1 problem homework for homework 7.
Oh, shoot. So,
Hooray!
how many, 1 problem, how many letters?
Oh, probably only 3 letters.
Oh, that's even worse.
Any questions or comments before we get started for today? Which ancient civilization was the best at algebra? The Romans, because whenever they had to solve for x, it was easy for them. They always got x equals 10. Say what?
Wouldn't that make you bad at algebra? It's like there's no.
No, because that's always correct. It was always correct that x equals 10.
The answer was always jobs.
Not for the road.
No. Anywho, so last time we kind of talked through some example of actually computing the Galois group, and then started talking about a special type of field extension, which is going to come into play in the next packet to give us a theorem that one might consider quite fundamental to our understanding of Galois theory.
The fundamental theory of Galois theory?
Perhaps. And so, but turns out, in order for that theorem to apply, we need to have 2 specific types of field extensions. One being a normal extension, one being a separable extension. Hush. So first up, normal extension, we started talking about last time, where extension L over K is called normal if every irreducible polynomial in K with at least 1 root in L must split completely over L. So we said that actually proving something does satisfy this definition is actually quite tough. Proving it doesn't, not so bad. What would be an example of a non-normal extension?
C over Q.
C over Q? So you're saying there's a polynomial with at least one complex root that doesn't split completely over the complex numbers?
Wait, no, never mind.
I'd say every polynomial splits over the complex numbers.
R
R over Q.
or Q over Q.
Or Q over Q. I think this is the one we did last time.
Was the one we did last time?
Yeah.
So why not just say Q adjoined for root of 3 to be different?
Sure, why not? So I claim this is a non-separable extension. The reason being, we can find a rational polynomial that has at least one root in Q adjoined fourth root of 3.
Why did you say non-separable?
Or, I meant
Did you mean
non-normal.
to, okay, I was gonna say, did you mean to say non-normal or is there something else we don't know yet?
Well, no, it actually definitely is separable, but it's not normal. The reason being, you could take a polynomial, I don't know, x to the 4 minus 3. That's a rational polynomial, has a root, fourth root of 3 in our extension. But it turns out it doesn't split completely. In the extension. So what would be another root of what? So what would be another root of x to the fourth minus 3 that over the complex numbers, let's say, that is not an element of Q adjoined 4 through 3?
I fourth root of 3.
I fourth root of 3. I is, or not I, but I fourth root of 3 is also a root. That's not in Q adjoined. So this would be an example of a field extension that is not normal, that you can have polynomials that have some roots in your extension, but not all of them. Or that doesn't split completely, at least.
Given the theorem that we were working on proving on last time, that means Q adjoined fourth root of 3 is not the splitting field for any function, right?
That would be correct, yes. Because we said last time, it's really hard to prove directly from the definition something is a splitting field, that every irreducible polynomial with at least one root has to have all the roots. It's easy to prove that for any, it's not too hard to prove that for any single polynomial, but proving for all of them at once is a wee bit trickier. So instead, we've got a theorem that gives us a much nicer way of being able to actually prove something is a normal extension. Which we started proving this last time, which said that a finite extension L of k is normal if and only if L happens to be a splitting field for some polynomial over k. So for instance, that would tell us that this, for instance, is a normal extension. Why? Because it's a splitting field. Over the rational numbers for f of x equals what, Jackson?
F of x equals.
Well, what would be a rational polynomial that has a square root of 2 as a root?
X. 2, that'd be x squared minus 2.
You got it. X squared minus 2. Yeah, turns out Q adjoined root 2 is a splitting field for that polynomial over Q. Because if you just adjoin root 2 to the rationals, then this thing will split into linear terms, into x minus root 2 times x plus root 2 specifically. So according to this theorem then, that tells us that this is a normal extension. Meaning any single polynomial, any single rational polynomial that has at least one root in Q adjoin root 2 must have all of its complex roots in Q adjoin root 2. So forward direction, we proved last time that a normal extension has to be a splitting field by explicitly constructing some polynomial for which it was the splitting field. And so last time we started proving the backwards direction, where if L is a splitting field for something, then it also has to be a normal extension. And we said we're going to let L be a splitting field for some polynomial g of x over k. And we want f of x to be a polynomial in k, be irreducible with at least one root alpha in L. And our goal is going to be to show that f of x splits completely over L. So in other words, if g of x has splitting field equal to L, f of x is some other irreducible polynomial, then having one root, alpha in L, means you have to have all your roots, or at least split into linear terms over L. Any questions or comments about this before we jump into the new stuff? So here's what we're going to do. We're going to make a fun lattice. And we're going to be looking a lot at field lattices in the next few classes. Spoiler alert. What we're going to do, we're going to let E be a splitting field. For f of x times g of x. So in other words, f of x times g of x, this is some polynomial that's going to be a polynomial in L. It's actually going to be a polynomial in K, but polynomial in L as well. And we're going to suppose that beta in E is a root of f of x, considered as an element of L. And our goal is going to be to show that beta also necessarily then has to be an element in L as well.
Wait,
L fuzz.
beta has. I don't.
We're assuming beta is we're going to show f of x splits completely by supposing beta
It's one of its roots.
is one of its roots and then showing that that root has to also be in L.
Okay.
To show, and if we can do that, that would necessarily tell us that, well, assuming beta is arbitrary, that f of x would split completely over L. Because E being a splitting field for f of x times g of x means that f of x must also split in E. It's not necessarily a splitting field because we don't necessarily get the norm minimality anymore, but E being a splitting field for f of x times g of x will mean that f of x necessarily does split over E. But we're defining it in this way because we also want g of x to split over the same E. Everyone okay? All right, here comes the lattice, because we got a bunch of fields going on here. We got ourselves a K. We got ourselves an L. We got ourselves an E. Where in general in this diagram, having an arrow pointing from A up to B just means that A is a subfield.
Instead of drawing a bunch of angled subfield signs.
Correct. We also have K is going to be a subfield, K joined alpha, which in turn is going to be a subfield of L adjoined alpha. Which, since L is a subfield of E, and alpha is an element in L, meaning alpha is an element in E, that's going to be a subfield of E.
Wait, if alpha is an element in L, then how is L adjoined alpha anything different than just L?
It's equal. But I'm including it in two different places to make a point that we will see. Check this out. Is also contained in K adjoined beta, where beta is this root we'd like to prove is in L, which is also contained in L adjoined beta, which is also contained in E. All right, you all ready for this? time for a good old-fashioned argument that in representation theory we call diagram chasing. Where we're going to look at what happens if you take a bunch of different arrows and have multiple routes that go to, multiple paths, let's say, that go to the same point.
Do you draw more arrows from L to L?
Sure, we could. In fact, well, I mean, here these are really equal. And our goal, and this is contained in here, our goal is to actually prove this and this are equal. Because if we can do that, then that's the same as saying beta is an element to null. So we could.
Does that mean we could put a
Oh,
line?
and actually, I just realized that we need these. So yes, Jonah, we are going to include those.
Is there no like line with a question mark over it?
Well, it's definitely
No, it's
a
definitely-
subfield.
It's definitely a subfield, but it's equality of this and this, that's the question mark.
Because we proved that.
Well, I mean, that's.
It's defined.
I guess it's just a function.
Alright, so before we start doing our diagram chasing, our goal is going to be to prove that L of beta equals L with doing this sort of diagram chasing. So to do that, we need to look at a bunch of degrees of various extensions. So first of all, we can say that since alpha and beta are both roots of the same irreducible polynomial f of x over k.
Wait, alpha's a root of x? Yeah. Oh yeah, because it's the one that we.
F of x
define
is
as
irreducible with root alpha, yes. And beta is also a root of f of x. The alpha is the one that we know lives inside of L. Beta is the one that we don't know yet whether or not it lives inside L. We know, though, that since alpha and beta are roots of the same irreducible polynomial, we can start using some of our previous theorems and say that k adjoint alpha is isomorphic k adjoint beta. And this came from, I forget what we called this one. It wasn't Snazzy Big Theorem, but it was like, you all had a name for this. Basically, it's the one that's proving that like if you do a simple extension by the same root of a polynomial, this is a few packets ago now, then the corresponding extensions that you get are necessarily isomorphic. The reason we want this though, k of alpha to be isomorphic to k of beta, is that's going to tell us that the degree of k of alpha over k has to be equal to the degree of k of beta over k. Done?
Wait, are all just saying that L and L beta are the same? Why not just do? And we know that L is the same as L joint alpha. Why not just do that there instead of trying to work out K?
Do what?
I mean, so if we know that L is equal to L joint alpha,
Yeah, these are equal.
and by the same reasoning, could we just do that L of alpha is the same as L? Is there why wouldn't this apply to L?
It would. But I specifically want to write it this way because this way is going to be useful for us here in a minute. Hold your horses. It'll all come together.
So alpha and beta are both roots of f.
Correct.
Um,
Alpha, we know, yeah, they're both roots of alpha. We know alpha and beta both live here in E. We know alpha lives in L. The question is, does beta live in L?
okay, where does G come into play? Do either alpha or beta have anything to do with G?
So far, no. So far, no, it doesn't. Nothing's come into play with G yet, but it's about to.
Okay.
So next up, okay, so we want this. This is going to be useful equality here in a minute. So let's talk about G though. We can say that since G of x, or not since G, since L is a splitting field for G of x, over K, here's a fun little algebraic fact. We can say that L of alpha is a splitting field for g of x over k of alpha. Same polynomial, but a different base field, k of alpha. L of alpha is going to be the splitting field for, or a splitting field, excuse me, for g of x over k of alpha. The reason being why this is why this becomes L of alpha and not just L for what our splitting field is because our splitting field necessarily needs to be an extension of our base field.
But since L of alpha equals L, isn't L?
Well, since L of alpha equals L, you're right. This actually does come out to be nice now that I think about it. But if we didn't know that alpha was an element in L, this would still hold true. Similarly, we can say L of beta is a splitting field for g of x over k of beta.
And then in this case, since we don't know L of beta equals L, we do need the.
In this case, yes, this is necessarily not equal to L. So this time we are saying something more substantial. But here's the thing. L of alpha is a splitting field for g of x. L of beta is also a splitting field for g of x. What do we know about splitting fields?
They're isomorphic. They're unique up to isomorphism.
Splitting fields are unique up to isomorphism. It's L of alpha and L of beta have to also be isomorphic. Thus, L of alpha is necessarily isomorphic to L of beta. Hence, the degree of the extension L of alpha over over K of alpha is equal to the degree of the extension L of beta over K of beta.
Can we just say that L is now isomorphic to L of beta because L of alpha is L? I don't
Yes.
know if that's helpful in particular, but
Yeah, you could. I don't think that's going to be super helpful.
can we say that it's equal to the extension, it's isomorphic to the extension, and therefore how could it possibly?
L is isomorphic to L of alpha by the fact that it's the same thing as isomorphic to L of beta. Yes, L is isomorphic to L of beta. You really want to use the fact that L of alpha and L are the same thing.
It really seems like that should help.
This is simpler.
Maybe it is, but at some point we need to use the uniqueness of splitting fields to kind of give us this result. Whether we
We
do
just
that,
did though.
well, yeah, but if we just replace all of our L of alphas with L,
No, I mean saying we use the uniqueness of splitting fields to get the isomorphism, and then just say, well, then that just means that L of beta is isomorphic to L. Does that mean they're the same because?
sure. Well, no, because that would just because they're isomorphic doesn't mean
But how can you have an
equality.
extension of a field that is isomorphic to the original field and isn't equal to it?
Oh my gosh! In the same way that you can have the integers be a proper subset of the rationals, and yet they have the same cardinality.
Okay.
You need.
Being in the case if these are finite fields, then yes, that would be done. But in the case of infinite fields, you can have fields that are isomorphic to a proper subset of themselves.
Subset
Okay.
plus isomorphism implies equality.
No.
Nope.
Like 2C is the subset.
Oh, okay.
Yeah, essentially that's what we're just saying. Like in the case of infinite sets, like intuitively it feels like it should be the case. Oh, if you are the same as the proper subset of yourself,
I get it.
then or a subset, then it should be a non-proper subset. It should be equal. But for infinite fields, which most of the things we care about, like these things are, that's not enough. Thanks.
So can we use that theorem of multiplication of degrees of these thingamajiggies, extensions, not these thingamajiggies, to say that therefore L of alpha, the degree of L of alpha over K is equal to the degree of alpha beta over K.
Oh, we're going to be using that theorem a lot here.
Okay.
I like it. Here's what we're going to do. L of beta over L multiplied by L over K. We're going to take the degree of bit over bop times the degree of bop over bit. And according to that theorem, I think you're just referring to, Seamus,
Yes.
what's this equal to the degree of?
L of beta over K.
L of beta over K. So we're saying the degree of this arrow times the degree of this arrow is equal to the degree of that arrow.
So,
But what else is equal to the degree of L of beta over K?
Well, also
Ignore the left hand, using the right hand side of the diagram.
L of beta over K of beta times K of beta over K.
L of beta over K of beta times K of beta over K. And here is where we're going to use these two things that I've underlined over here. The degree of L of beta over K of beta is equal to the degree of L of alpha over K of alpha. And the degree of K of beta over K is equal to the degree of K of alpha over K. Because this equals that and that equals that. And how can we combine those into a single degree of a field extension? Isaac?
L of alpha over K.
L of alpha over K. Which in turn Emily Rose, what's the relationship between L of alpha and L?
they're the same. Ooh.
Oh.
Because
Here we go, we're finally using that result of yours. So what does that tell us? We know that L of beta over L times L over K, the degrees of extension, is equal to the degree of the extension L over K.
L of beta over L is 1.
L of beta, degree of the extension L of beta over L, has to be 1,
Which means that's the same.
which means L of beta equals L, which in turn implies it is an element of L.
Are we back to using the subfield definition of field extension?
We are for this.
Okay.
You could just use them, do everything with like these one-to-one homomorphisms. It ends up being the same proof, but like twice as long and like 3 times as messy. So I'd rather not if that's all the same to you. We're only going to that more generalized definition when we absolutely need to, such as to like when we needed it to guarantee the existence of splitting fields, for instance. So that means beta is an L, and since beta was an arbitrary root of f of x over E, that means f of x splits completely over L, which in turn implies L over K is 1. As the prophecy has foretold. Woo! Whew. It's a bit of a long one, but I also think this is a fun one in that you're really just kind of bouncing back and forth between different subfields in this diagram. And then just kind of using all these different field extension properties and kind of relying a lot on this uniqueness of field extensions, uniqueness of splitting fields to say certain things are isomorphic and so they have the same degree. But all comes out nicely. Yeah, questions, comments, concerns? Alrighty, so here's a fun corollary of this. That in a normal extension, if you ever have 2 roots of the same irreducible polynomial, there's always a K automorphism mapping one of those roots to the other root. Which is kind of something we've been using for a while, saying, oh hey, you have all these roots, there's always going to be some automorphism mapping one to the other, and such. We never actually had a formal result up until now that tells us not only does the roots of the same irreducible polynomial have to map to other roots, but given any two roots, there's always is going to be an element of your Galois group mapping one to the other. Let's write this down. So if L is a function, I'm just going to say L over K. L over K is small. And it's a finite degree extension. And Z1, Z2 are roots in L. Scram. Of an irreducible polynomial in K of X. Did I not name it? Then there exists a K automorphism phi of L with phi of Z1 equal to Z2. Someone remind me.
Why does Z2 have a bar over it?
It doesn't, it's just, it didn't connect the way I wanted it to.
Okay.
So, can someone remind me, what's a K automorphism? Andrew?
And automorphism of L that fixes K.
Yeah, it's an automorphism, so it's a isomorphism from L to itself that fixes K, meaning every element in K gets mapped to itself. Turns out this is a consequence of this theorem right here. That if you have a normal extension, it turns out to be a splitting field, which is what's going to cause this to happen. But no matter what's going on in your life, Eleanor, Galois theory will always bring out the giggles. It would seem. So, we're going to cite a very old theorem at this point and say, by an old theorem,
Which one?
it's going to be clear, like, let me finish my sentence, gosh. By an old theorem, since Z1 and Z2 are roots of the same irreducible polynomial.
I should have put that on my homework, because I definitely cited an old theorem, and I'm pretty sure I did put by theorem, but
I mean, this is one of these theorems that doesn't have a name. It's not like
We give it one.
It's so hard
It
to
is
cite all the theorems that
Says
you've given us that have no name.
I mean, I could just call them all like theorem 7.21 from the book, but
Is that what it's called?
no, this is not no, this is like a chapter 3 or 4 theorem. Since Z1 and Z2 are roots of the same irreducible f of x in L over K, we know there exists a K isomorphism psi from K of Z1 to K of Z2. So basically just saying, if you have two roots of the same irreducible polynomial, then extending K by those roots gives you isomorphic copies of, gives you isomorphic field extensions, I should say. And part of how we prove that is we actually prove that you can form an isomorphism that does this in a way that's a K isomorphism, meaning every element in K gets mapped to itself, which is going to be important for doing a K automorphism of L here in a minute. Alrighty, then from our theorem, I'm not going to write that part out because you're all just going to make fun of me.
I want to make fun
Then since L over K is normal,
by the old theorem.
let's just buy one of our assumptions here. We know L is a splitting field.
Well, it's not present, is it? Must be.
You're not normal. L is a splitting field for some g of x over k. So this is just using our theorem we just proved that normal is equivalent to splitting field for something.
Which old theorem is that?
The one that's still on the board, that's not an old theorem anymore, that's a new theorem. This is literally a corollary to the thing we just did.
What's called the current theorem?
And because of, then by the I hate Parker theorem, since L over K is normal. No, that would be giving you too much credit.
Oh,
We're at the point in the year where we start naming things after Parker.
I almost had it.
I'd like to wait at least one more week before I get to that point. So L is a splitting field for g of x. All right, Parker, what do you think of this? Then L is also a splitting field for g of x, an element in, wait for it, k of z1 adjoined x,
Yay.
and k adjoined z2 of x as well.
That will do it.
That's right. We have a polynomial ring over field extension k of z1. And basically this just comes from the fact that if L is the minimal field extension over K that contains, for which g of x splits into linear factors, it necessarily follows that if you consider g of x the same polynomial in this larger field, the splitting field for g of x over that field would just be the same thing. Technically, this would be L adjoined z1, and this would technically be L adjoined z2, but Emily Rose using z1 and z2 are already elements of L from the fact that L is a splitting field. We know that that'll come out to the same thing. Are you doing okay so far? Elma?
This would not necessarily work if f of x were not irreducible, right?
If f of x was not irreducible, then no, it would not. Because then we would, well, this would not necessarily work, this bit right here.
And z1, z2 would not necessarily be in L.
Right. So, now we're going to use, so, now we're going to apply our theorem that was the uniqueness of splitting fields. The one we didn't actually prove because I get fed up with all the abuse I got. Abuse? Yes. Our splitting field uniqueness theorem. There, look, I'll name this one. Psi can be extended into a K isomorphism phi going from L to L. Why? Because L is a splitting field for g of x over K adjoined z1. L is also a splitting field for L is also a splitting field for K adjoined z2. So by our uniqueness of the splitting field, we know that we can form an that any isomorphism from K of z1 to K of z2, i.e. psi, can be extended into an isomorphism from our splitting field of K of z1 over K of z to our splitting field over K of z2. Which in this case just happens to be L in both cases. So we get an isomorphism from L to L, i.e. an automorphism of L that fixes K.
Isn't it actually a L adjoins Z1 to L adjoins Z2?
It technically is, yes.
I literally put that in my notes.
Well, I'm glad you did that.
Because it makes more sense.
Look, I could laugh.
No, it doesn't. How are you gonna keep track of what's the same and what's not? They're all named different things.
They're the same thing, but they are
Oh,
mapping
that's not a
differently.
smart
I mean,
What?
Alright, I'm all chopped back up. Let's do this. Any questions or comments of this theorem? So basically, what this theorem tells us, we had a previous theorem that tells us if we have some k automorphism of L, it has to map roots of irreducible polynomials over k to roots of the same irreducible polynomial necessarily. This theorem kind of goes the other way and says that if you happen to have two roots of the same irreducible polynomial, you're always going to be able to find a k automorphism. In other words, an element of the Galois group that will map any one root to the second root, given any two roots to start. Questions?
Pretty useful.
I don't.
Okay then. So that's all I have to say about normal extensions for now. So let's go to separable. So a separable extension, kind of nice. Basically one where your minimal polynomials don't have any repeated roots.
Oh, nice.
We're gonna bring back an old friend for this discussion. A very old friend from like week 2 of the semester. Old friend.
Is it an old theorem?
Yes.
Oh, are we calling it the old theorem?
No, we'll call it the Andrew theorem for reasons that I hope make sense. Eventually. Now, an algebraic element alpha in field extension L over K is called separable over K. If its minimal polynomial in K has no repeated roots. In some splitting field, I should say. And then L over K is called a separable extension. If every element alpha and L is separable over K. So in other words, L over K, where every single element in L, if you take the minimal polynomial of that element over K, you don't have any repeat roots whatsoever. This is definitions. This is just definition of what it means to have a separable extension.
Now, are we going to do examples?
Would you like to get up and teach this class?
No, I want to do examples because I'm having trouble picturing this.
Sure. All right, let's do an example. Here's one. Q adjoined root 2, root 3 over Q. Now here's my question to you, Emily Rose Willis. Is this separable or not? Is this, in other words, is this an example or a counterexample?
I think it's an example, because.
Turns out it is an example.
Yeah.
It's a little hard to show directly, but it's not too hard to show for any individual alpha. It's hard to prove it for an arbitrary alpha. Less hard, more tedious, I would say. So it's just an example. Let's say alpha equals square root of 2. That's an element in the extension. So that's going to have a minimal polynomial, x squared minus 2 in Q. And in a splitting field, for x squared minus 2, like, I don't know, for instance, Q adjoined root 2. x squared minus 2 factors into linear terms, hey Parker,
Yeah, what's up?
how does x, not much, how are you doing? How does x squared minus 2 factor in the splitting field?
Well, I'm pretty sure it factors into x plus, or not, well, I guess I should just say x minus square root 2 and x plus square root 2.
Hey Matthew, do you see any repeated roots here?
In my head, no.
How about on the board where it's located?
Like, no, but I don't know if there's some gimmick where you're gonna be like, well, technically, like root 2, it's like of the same culture as like minus root 2.
Same culture.
Like,
But I say repeat.
I've been clickbaited one too many times.
When I say repeat roots, do you see the same linear factor showing up more than once in this factorization?
Yes. Right? A linear factor means like it's kind of like a base.
The same linear factor. The answer I'm looking for is no.
Wait, what do you mean by linear factor? Like, wouldn't you mean that like
There's
oh,
no
it's like a base?
Like you don't have like this occurring.
Oh, okay. I think
Like
you meant
where x minus square root of 2 occurs multiple times as a linear factor.
I think you meant like if like root 2 is a base, like you could go into like the negative realm.
Gotcha. Now, when I say repeat roots, I literally mean the same thing being a root more than once, which doesn't
Okay,
hurt.
because then everything we would have been doing would be non-separable.
This is no repeat roots. So what does this tell us? This tells us that alpha is separable over q. Why? Because its minimal polynomial over q doesn't have any repeat roots in a splitting field. If you take some field extension where this splits into linear terms, none of those linear terms are going to occur more than once.
But if we did the same thing with the smaller one being q adjoined root 2, this would not work, right?
It would. Like this being q joined root 2?
No, the other one.
Why did we start with Q?
What's the other one?
That just the q by itself. If
Oh,
we
like
added-
this?
Yeah.
Oh, I mean it's minimal. Well, that thing's well then square root of 2's minimal polynomial will just be x minus root 2, which
Yeah.
I don't
Oh,
think
which
that has
also-
any repeat roots.
So,
So I think that would still check out.
I want to count.
Jonah?
So what's an example of something that is not separable?
Yeah.
Good question.
Yeah.
Emily Rose, do you know of any?
Well, I was going to originally, I had another question.
Alright, what's your other question?
Why did we start with Q adjoined root 2 and root 3 when we only used the splitting field to show that alpha was separable?
Because I wanted to make a point that that this itself doesn't have to just be the splitting field for root 2
Okay.
or anything.
And
Or
the answer
x
to your
minus 2.
question is no, I do not, and that was why I wanted to do examples.
Eleanor,
C over C.
C over C. That is a separable extension.
No.
Certainly,
Wait.
Well, 'cause everything.
Literally every element is C.
Oh.
Yeah, if your field is the same in both cases, then literally everything's minimal polynomial is just x minus that term, and that has no repeat roots.
Okay, just kidding.
I was just testing you, Kirsten.
Good job. You guys put this. Matthew?
Could you do something gimmicky like q pi over q, and then just like since there's like infinite like. you can't get
Typically
them
we want to look at algebraic extensions when we're doing these.
Say that can be
What defines algebraic then?
Every element has a minimal polynomial.
Oh, okay. Yeah, then.
So like pi is not a root of any polynomial in Q, so
okay.
that's not algebraic. In this, I'm going to look at the context of algebraic extensions.
What if we start hacking together
What if we say q adjoined 2?
like multiplicity?
Could you
So
construct
start just make a minimal or make a polynomial and then find what it's a minimal polynomial for.
What if you did?
Do what now?
What if
Say
you
that
like,
again.
Make a
I cannot
polynomial with
understand.
multiplicity of more than one.
Like what if you did x minus 1 squared and then x plus 2
And then
or x
construct
minus-
something for which that's the minimal polynomial.
Yeah.
Bleh.
I was
No. Just no. Because then you have to actually go through and prove it's the minimal polynomial, and you're going to have a very hard time doing that if you approach it from that direction.
it's tricky for me just thinking about it to come up with an irreducible polynomial that also has repeated roots. Because if the roots repeat, at least in the numbers I'm most used to working with, which is probably my problem, I'm not thinking out of the box enough, that usually means it's not irreducible.
You would think.
This feels related.
Andrew,
Well, everything.
I brought you up for a reason earlier, because you're going to be useful in our counter example.
I don't have a counter example. I was just gonna say everything is separable over R, or every complex number is separable over R.
This is true. How about this? Say Z mod P
Oh,
that joins some other variable T as an extension of Z mod P over, say, some power of T.
Scallop.
Oh,
God.
No, because I want to
Oh,
reserve X for talking about the minimal polynomial of T.
See, the problem
So let's call this L, let's call this K.
Wait, is L-
You might think I'm being mean to you, but this is like the simplest counter example of or non-separable extension I can find.
It might be easier, but
Is
it
there a
requires a
process
divine
of-
revelation from on high of what in the
No.
world you just did.
So what's going on here? Basically, we're looking at rational forms where your coefficients are aligned in Z mod PZ.
Okay. Is Z mod P adjoining T bigger than?
Yes.
Z mod P adjoining T to the P?
Yeah, because anything that's a power, this is a subset of that because anything that's a power of T to the P is necessarily a power of T, but things that are powers of T are not necessarily powers of T to the P.
Like
I
see.
I forgot.
T is in the first one, not the second.
Correct.
Oh, so since it's, if C here prime.
I should hope so. Otherwise, Z mod P is not a
Oh,
field,
yeah,
and this
right.
totally breaks down.
That would be fun.
So let's take a look at this. In K, or at least in K adjoined X, so in Z mod P adjoined T to the P, rational forms of T to the P, polynomials over X. T, which is an element in L, has what minimal polynomial? So in other words, what's the polynomial of smallest degree that in this thing, that T will be a root of? Where the coefficients can only come from Z mod PZ and have powers of T to the P. And this sort of gets into why I wanted to use T here and not X, because we're going to need X to show up for terms in the polynomial. Lincoln, look like you have an
I
idea.
don't know enough number theory.
Like X minus T to the P squared or something?
Oh,
Like that. Is T to the P is not a root. Or T is
T
not
to
a
the
root.
P, sorry, I meant T to the P squared. But I don't actually know.
where T is a root?
X to the P minus T to the P?
X to the P minus T to the P.
Oh,
Yeah, because T is a root of that, right?
Yeah.
It should be. I sure hope it
If
is.
it's not, there's a problem.
But there are more than that.
So Andrew, why am I invoking your name in this example?
I get it.
Eleanor, why am I invoking his
Freshman
name?
exponentiation.
Freshman exponentiation! How about that? Remember back when we were literally our second packet of the semester, we were talking about fields of characteristic P?
Yeah.
This is a field of characteristic, well, these are fields of characteristic P. So thing to the P minus thing to P is X minus T to the P.
That's crazy. I was looking
This
at
has some repeat linear terms in it, doesn't it?
So many
It has P, I would argue.
I do not like that. I do
This
not
is
like
so
that.
fun.
it's
I love
It's
this.
irreducible.
That is so bizarre.
Why?
I mean, it kind of makes sense that it's this bizarre because I was talking about how it doesn't make sense with numbers we normally deal with.
Yeah, these are funky numbers too. Considering they're
There
not
are-
actually
there are no
numbers.
numbers.
There are no numbers. These are just
P is a number.
They are numbers.
Okay, P is a number.
No, they're
But
all
T is not.
representative of numbers, but there is no number on this board.
I mean, they're not numbers anyway.
Really?
They're not
P is
numbers.
really the only thing that's a
Z-
number
Zmod-
on this board.
They're cosets.
Yeah, exactly.
They're not
That's what I
numbers,
was
they're
trying to
cosets.
say.
So this is really weird.
Well, they are cosets.
They are cosets, yes.
Jonah.
Are there extensions of Q that are not separable?
Good question. No. In fact, I'll generalize what you just said. Our next theorem is going to be to prove that in any field of characteristic 0, all extensions are separable.
What's the characteristic?
Not sigma.
So it turns out the reason I had to get pretty nasty for a counterexample to separable is because in all the things that are nice and easy to work with, like extensions of Q, for instance, it turns out everything is separable.
Yay!
You have to have you have to be looking at weird fields and weird field extensions like this one in order to be able to
I
apply
did
that.
notice we've never worked with an example where you have multiplicity of limit terms.
Yeah.
That's because we've mainly been working in examples over Q, and over Q,
Can't do it.
everything is separable. You aren't going to have everything.
over Q to the sum root of 2 or the sum root of 3.
Hey, now, can we do? Yeah, no, that was
Or
root of
5.
three. Dang it, that was root of 3.
Dr. Gabler brought up something like a Q extends square root of 5 for a discrete math thing, kind of indirectly, and I'm like, if the theorem that you put on the board is not true, all of the stuff we've done in Galois theory doesn't work.
Yeah, pretty
That's
much.
our single example.
I mean, it's done like Z adjoint square root of -5 and stuff. So let's look at this theorem coming up. It's basically the theorem says field characteristic 0, every field extension is separable. Which, as a consequence, would immediately say that since Q is a field characteristic 0, Jonah, yes, every extension of Q is separable.
Okay, just what's an example of a field with characteristic 0 that is not an extension of Q, just because all the ones that we've been talking about usually have been.
It's not an extension of Q.
Yeah.
That is not a field.
Oh. Which one of these is a field? Because when we were talking about characters.
The complex numbers.
I mean, that's an extension of Q.
Oh, yeah, that's right. Never mind.
Technically, every field characteristic 0 is an extension of Q if you allow for the contains an isomorphism copy of Q. Like, more generalized definition, I'm pretty sure. And that's just because if you're a field, you gotta have one. No, because well, no.
There are certain
You can have matrix groups that form groups under addition. You can have matrix groups that form
But not both.
groups under multiplication. Having both very much limit your options. Do they exist? Sure. Take the zero matrix. The trivial one. That's a field.
Not an extension of Q, I guess.
It's not really a very interesting
Characteristic
book.
0. Well,
And
characteristic
any L
1.
over K is. So we haven't actually talked about this in like several months at this point. What does it mean to have a field of characteristic 0? Andrew?
It means that if you take 1 and you add it to yourself a bunch of times, you never get 0.
Essentially, yeah. If you keep adding 1 to itself over and over, it's never going to loop back around to get 0. Contrast that with something like Z mod 5, for instance, where if you add 1 plus 1 plus 1 plus 1 plus 1, you get to 0.
I love adding 1 to itself 5 times and getting nothing.
1 plus 1. Ooh, Alright, here we go. So this proof is going to do something we haven't done all semester in this course, I don't think. Something that you do a lot in other math courses. Close, we're going to take a derivative.
Oh!
my gosh.
I was close.
Yeah. So let's start off by letting alpha be an element in L have minimal polynomial. Call it m of x equals a sub n x to the n plus bit plus a1x plus a naught. our goal is to show that, m of x has no repeat roots. So, I'm going to do a little proof by contradiction. So we're going to suppose that m of x is not separable. So in other words, we're going to assume that m of x has a repeat root.
Isn't it alpha is not separable? Meaning that m of x is a repeated root?
And
Because alpha, it says
oh, sorry, that. Suppose that, yeah. Yeah, sorry, that's what I meant. Good call. Suppose alpha is not separable, yeah, polynomials. It's not polynomials that are separable or not, it's either the extension or an element in the extension that can be considered to be separable or not. So let's assume that m of x has a repeated root beta in some splitting field. Let's call the splitting field, just want to make sure of something real quick, we'll call it Parker. I'm calling it that because we're not going to refer to it for the rest of the proof.
I thought you said we were waiting till next week to name things after him.
I've been driven over the edge.
I didn't even do anything.
I mean, in my notes it just says E, but I decided to spice it up because we're not going to actually be referring to the splitting field.
I'm spicier than E. Let's go.
No, you're not.
Oh.
Alright, back to E.
You messed
So-
it up again.
M of
That
x.
means you gotta use me later.
M of x has a repeat root. What does that mean? What does that mean if beta is a repeated root of m of x? What else? What other polynomial is beta necessarily going to be a root of?
M of x over beta.
Over x minus beta.
Over x minus beta.
I'm sorry,
Yeah.
my brain squared.
How about m prime of x?
Wait, really?
Yeah.
Yeah, because when you take a derivative, you lose one copy of all your roots, right? For a polynomial.
Copy.
So like if m of x
Oh, yeah, I definitely
is something like x minus 5 to the squared,
Uh-huh,
when you differentiate, you're going to lose a power of x minus 5.
uh-huh.
But if you have more than one to begin with, you'll still have one there. And that's the same as if you had a bunch of other stuff attached. Because then you get f of x plus x minus 5 squared f prime of x. In other words, if x minus 5, let's say, is a repeat linear term here, then it's still gonna, you can still factor it out of the derivative.
You don't necessarily lose the copy. It might work around and you get it back, but you at least have one left. That's all we're relying on.
Correct.
Okay.
You at least have one left, yeah. So then we can say, how's that with calculus today? Then in k of x, m of x, I'm just going to pretend I didn't hear what that was because I kind of didn't. I have a common constant factor. Doesn't even need to be a linear factor necessarily. We'll say d of x. For the common factor that m of x and m prime of x have with each other. So here's my problem. M of x is a minimal polynomial. What property do we know minimal polynomials have?
They ought to be irreducible.
They ought to be irreducible. So if m of x is irreducible, and d of x is a factor of m of x,
D of x can't be an element in k of x.
it can be.
But I mean,
You could have m of x and d of x are equal to each other, for instance. But it does mean that d of x is either equal to k of x or it's a unit multiple thereof.
you said equal to m of x, right?
Is that not what I said?
You said either equal to k of x or a unit multiple
Oh,
there.
sorry, yeah, I meant m of x.
It's equal to the entire.
Then since, we did since m of x is irreducible,
At this point, I wouldn't be surprised.
you would be surprised by what?
I would be surprised if it were like, oh, it should be, well, it's just gonna be d of x is equal to the entire field. Like, we've been throwing around, like, throwing fields into algebra at this point so much that it's like, oh, okay, yeah, we'll just put
I know,
we'll put a field
d
in
of x
the
must
equation.
be a unit multiple
There's a field in this polynomial.
of k of x, implying k of x divides k prime of x.
Oh, no.
Because if d of x is the unit multiple of k of x, and if d of x divides k prime of x, that means k of x has to divide k prime of x.
What is
K?
a K?
K?
M
Yeah.
of
M of x, oh my god! I eliminated Parker from the proof, and I love that so much that I started trying to introduce myself. K in places it shouldn't be.
Wait, hang on. We still have K
You
to
still
the
have
X.
one.
This is what you deserve.
No, that's correct.
Yeah,
I think
yeah,
this is now correct.
This is what
Wait, I thought d of x was the root of m prime of x, not.
It's a common factor. D of x
Oh,
is a factor of m of x and m
Maybe
prime
it's
of x.
both.
Which is gonna be like x, it's gonna be x minus beta, maybe times something else, is that?
Is what equal to what now?
Why did we do d of x
Because
rather
there's
than
nothing
saying
to
x minus beta?
usually,
We could have it.
That's fair.
there's no
I
numbers
choose
usually.
something
You could take a linear factor, depending on the function, maybe d of x is you could make d of x non-linear.
Number on that
The
board.
degree of d of x isn't important in and of itself.
Is it m prime divides m of x or m of x divides m prime of x?
We
M
don't
divides
need
m prime.
We could just
But-
say there's numbers and then let the rest get filled something.
Is this where the contradiction is?
How many functions do you know of that divide their derivatives?
None, because derivatives have a smaller
No,
degree.
wait, e to the x.
Unless,
E to the x.
It's zero.
how many polynomials do you know of that divide their derivatives?
Unless
Good
they're-
catch. Good catch. I didn't. Yeah, good
Unless
catch.
they're-
There are lots of functions out there.
I can.
Unless they're constant?
Yeah.
I suppose.
Or they're constant. Can you have a constant minimal polynomial?
No.
Degree zero extension.
Degree zero extension. Yeah. So here's something. Yeah, technically you can in a weird field. So let's see. So this requires, the only way this can happen, sum up, is if your derivative is zero.
Hey, wait a minute. That would mean that it's like a constant or something.
Yeah, well that would imply you'd have, oh gosh, who remembers how to do the power rule?
Huh?
What is the derivative of this thing?
A1.
We get n
Or wait,
times
wait.
an x to
Oh,
the
that, yes.
Oh,
And
minus 1.
I
Yeah.
see.
Times
Nice.
n minus 1,
You made it sound
a
so
n minus
difficult.
1 times x to the n
I've
minus
never
2
heard it
and so
called
on.
that before.
Plus bit bit bit.
Where did you learn
Plus-
calculus?
The power rule.
Plus a1.
I didn't realize what, that we
That's
were
just a legitimate question, where did you learn calculus? Physically where?
Under a grid.
I'll talk to you later.
So here's the derivative of this,
Yeah, learned introductory analysis.
which, if this is the zero polynomial, that means that n times a sub n equals n minus 1 times a sub n minus 1 equals bit 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 equals a1 equals 0. Because if this is the zero polynomial, every single term in it has to be 0. Lincoln?
Well, sorry, I was just saying, do we even need an a sub n because it's minimal? So it has to be monic, right?
Oh, true, yeah.
But we're putting it in there.
Yeah. Take that. Technically a sub n has to equal 1 here, because if this is a minimal polynomial, then it has to be
So
monic.
that means that n must equal 0.
Not that n equals 0, but that well, yes,
It means that
Yeah.
n has to equal 0.
It
Zero
means-
divisors here.
no, let me rephrase. It means n times 1 has to equal 0. Meaning if you add 1 to itself n times, you get 0.
Which means it's cyclic.
Which means, and this is where it comes into play,
That's actually.
everything we've done so far works in characteristic non-zero.
Worry about zero.
Here's where it breaks down. We need the fact that we're in characteristic 0 to say that this implies that a sub n equals a sub n minus 1. a sub 1 equals 0.
Which means that n equals 0, actually.
But if our characteristic is non-zero, that means.
So what does that tell us about m of x then?
X is a constant.
I was hoping I'd get you to say 0. We don't know m of x is 0 from this, because we still don't know if this term is 0. But we do know m of x is constant, and that can
No,
Thank you for that. Thank you for that contribution to our
that
class.
was like a squid dying.
You're very welcome.
Then m of x is constant.
I
A
almost got you to
contradiction.
say it.
Hence, what do we contradict? Alpha must have been separable. I guess maybe I should technically then have one less and saying thus L over K is separable since alpha was arbitrary or something.
You probably said this by mistake. Why do we know that all the coefficients have to be 0 and that none of them cancel out? Like positive, negative.
Because this is, we're not just taking this equation and solving for x. We're saying this polynomial is literally the 0 polynomial
so
entirely.
You could represent it as.
So basically,
Yeah, it would be worth. Yeah.
this has to be 0x to the n plus 0x to the n minus 1 plus 0, blah, blah, blah. And saying those two polynomials are the same everywhere means all the coefficients have to be 0. Jonah,
How do we go from the bottom, second to bottom line to the bottom line again?
here to here?
Yeah.
The fact that we're working over a field of characteristics 0. Because n times a sub n, by definition, this is just a sub n plus a sub n plus plus a sub n, which is the same as a sub n times 1 plus 1 plus plus 1. And if that's equal to 0, this is never going to be 0 since we're in a field of characteristic 0, so that would have to be 0. And same for the other coefficients. Or I did kind of go through that pretty quickly. Does that make sense?
Yeah. So we also know that a sub n is 1.
We also know a sub n is 1.
You say that.
Yes.
Yeah.
Except we just proved a sub n is 0. Checkmate.
Show us the trivia.
Well, no, it just means we have a contradiction. It just means something's gone wrong. This thing can't have been separable in the first place. Or this thing can't have been not separable in the first place.
It can't have been inseparable.
Alright, so where do we go from here? One last page and I'll let you go. Don't worry, this one's very short. A field extension that is both normal and separable is called a Galois extension.
Oh, name drop.
There you go.
Go, Chris.
Good point.
It turns out that Galois extensions will have some pretty nifty properties.
Yeah, it will.
Like having Galois in the name.
Yeah, like that.
And be normal and separable.
L over K is an online separable. We say L over K is a Galois extension.
Do we have to pronounce it like that?
Yeah.
Galois extension. And we're gonna have a lot to say about that on Thursday. I'm done. Get out of here. So on Thursday, we're gonna come back and we're gonna do like one example of the whole class. It is going to blow. Let me rephrase it. It is going to knock your socks off. Eleanor, Emily Rose, wear socks to class on Thursday.
You don't want me to blow my flip-flops?
And Jackson too. And
Everyone's wearing socks.
Why won't you blow
it'll do that too. But
No.
it'll do that too. But like, but at some point on Thursday, I intend on taking my socks off just to make a point.
Oh! You're letting the
All
dogs,
right, no, I wouldn't.
you're letting the dogs out?
Well, the dogs were let into my class at like
Oh, that's
105. Like I was like halfway through 105, my 8 o'clock section. Oh, bye Lydia, have a good one. In the
Hi,
video.
Lydia.